Thank you.
Yeah. So thank you, Catherine. And now what I'm going to do is I'm going to talk about another paper, another work which I've done. And this one is uh, a similar work. In principle, again, this work also uses galfit. Okay, so galfit is the common factor between both these things, and I can show it to you how you can use it in such a different way in this thing. So all of you have already studied about AGN, right? So AGN are active galactic nuclei, right? So you basically have a compact region which is sitting at the center of the galaxy, which is very, very bright. And it's basically, it is non-stellar luminosity which is coming from it, which is observable in the radio, microwave, infrared, ultraviolet, etc., gamma ray, X-ray bands. And you can catch it in that, and it's non-stellar emission. And that's what's called an active galaxy. Now, what we did in this work was to study the G, that is the galaxy in the AGN, to basically study what is an active galactic nucleus and what are the kind of galaxies in which you actually see active galactic nuclei, right? So the study was basically to study the G in the AGN. Now, there are various different kinds of AGN. So if you actually classify AGN, the broadest classification is what is called radio quiet and radio loud, means what is observable in radio as faint and bright. And then there are a whole category of radio galaxies. And if they're the radio quiet ones, you have CFERTs, you have QSOs, you have different kinds of AGN. I'm not going to go into these details, but this was just to give you an idea of what AGNs are about. So like I said, the question we were trying to answer in this work was what is the morphology of AGN host galaxies, right? How can we actually study which are the kind of galaxies which host AGN? Now for this, the data set which we used was something called GOODS. So GOODS is a Great Observatories Origins Deep Survey, which basically included all NASA big observatories. Now, just for the benefit of students, I will tell you that in astronomy, there is a lot of archival data available, which is a lot of data which is available from the best of telescopes, which includes, for example, Spitzer, Hubble, Chandra, Herschel, XMM Newton. These are all very, all of these are space-based observatories, which gives you excellent data, and the data is freely available online. So the beauty of this is that you can always access this data free of cost. There's no charge for it, and there's no proprietary problems with this. Everybody can access this data. So actually, recently, I actually did a 6-month project with the IAU OAD on astronomy from archival data. Me and my husband, together with this project, we had a lot of lectures. So we have some 73 lectures online on YouTube. And students last weekend, they presented all their projects, which they did using archival data. And now for the whole year, we have another project, which is called Astro Sprint, again, which is supported by OAD, with which we are again going to talk about research projects with archival data. So we actually teach students to do some Python coding, as well as to do data analysis, use virtual observatory tools, and various things like that, so that they can access this data. I'm telling you all this because all of you students who would like to do projects using archival data, this is the best quality data which is available to you free of cost just on the internet, right?
Okay.
So
Thank you.
you can do this kind of work very easily. I mean,
Yeah.
since you have access to data, then you have to worry about what to do with it, right?
Of course. Yes. Yes. I have a question. Maybe you could briefly talk about what kind of data does Spitzer give, Chandra, Herschel, they're in different wavelength bands, right? So
Okay, sure.
thank
Do
you.
you want me to show them the websites, or I just tell them briefly?
Yes. Yes. Maybe that sounds interesting. Thank
Yeah.
you.
So, for example, if I can, here is my browser. Sorry, I'll just open my browser and 1 minute. Yeah, just a sec. So what I would actually like to show you is that, yeah, this is it. Okay. So what you can actually see is that there are various space telescopes. Okay. So the most popular and well uh, known space telescope is obviously the Hubble Space Telescope. Now, the Hubble Space Telescope, right, it was launched in 1995. And you can actually see that amongst the best pictures which you would see in astronomy are images which you can get from Hubble, right? And there are various images which you can get from the Hubble data for various kinds of objects. See, look at these. These are all beautiful images which are got using Hubble telescope. Now, the Hubble telescope actually, so for the archival data, they actually have a site called MUST, which is HST, which is the this is the site where you have the data for Hubble Space Telescope. This is the Mikulski archive for space telescopes. And actually in this, they've included a lot more space telescopes. So HST lies over here, and you can actually look for a target. You can look for an object. For example, you choose M51, right? A galaxy called M51, and you can actually search for it. And it will actually, this is M51, and it's telling you what is the data it has on M51, right? So you can see this is one of the cameras on HST, which is called WIFPIC-2. So this is WIFPIC-2. There's NICMOS. NICMOS is a near infrared camera on HST. So this is the NICMOS camera. And then there is ACS data, etc. So you can actually see it. If you click over here, you can actually see a preview of the data. So this is a preview of the data, right? And what you can actually do is it gives you, see, it gives you various details about this image, which you can see over here. This is M51. It's telling you the instrument, ACS. It's telling you the filter, which is this filter. This is 555 nanometers. This is the exposure time. This is the RA deck. This is the object, etc. And this is also telling you what is the work that was done using these images. Okay, so these are all the publications which were done using those images or which are referring to those images, right? Now, you can also, so similarly over here, like you can see, you can check up other data also, which is available using ACS data. This is other images, and you can pick up specific objects which you need. Now, this archive, it is basically deals with all space telescopes, and therefore it not only has Hubble data, it also has a lot more other data. I'll show that to you. So for example, like I said, you have Hubble data. Along with that, you have even Kepler, if you've heard about the Kepler. So you have Hubble Legacy Archive over here. You have the JWST data will come over here, which is going to be launched hopefully soon. There is K2, which is the the follow-up mission of Kepler. So there's Kepler and K2. There is the Pan-STARRS data, which is observations of in 5 different bands of the whole sky. You have the TESS data, which is very good if you are interested in doing exoplanet. So if you're doing exoplanet data, old ones are Kepler and K2, and the newer data is the TESS data. In X-ray, there is the XMM. And then there are, there is Galax, and Galax is in ultraviolet. So you can access all these. This is IU. This is, there are various other, telescopes. All these are individual telescopes, right? With which you can actually access their data using the Hubble archive, right? And on this, there are very nice, tutorials, etc. So if you do not know how to do it, this is showing you where the high-level science products are lying. And there's very good online help also. So in case you have any doubts or any questions, see, these are all the websites, this thing, data sources. In case you have any websites, they're also very helpful people. You can even write to them if you have some questions or some problems, right? The other data which we saw in that was what is called Spitzer. Spitzer is also a space telescope, and it basically observes in the near infrared, in the mid infrared. And the mid infrared, it's basically doing 4 different bands, 3.5 microns. See, I'll just show you. So this is the Spitzer telescope, which you can see over here, which observed in the infrared, right? It's a 2.5 meter telescope, which is out in space. and it is basically observes in 4 different bands. You can find various details about it over here. And the instruments are basically these. There is the IRAC, which is the main instrument, which observes in 4 bands, 3.6 micrometers, 4.5 micrometers, 5.8 and 8. There is a spectrograph. There is the MIPS. The MIPS also observes in 24 microns. This is further infrared, right? And Spitzer has a website also where you can access its data, right? Similarly, there's Chandra. Chandra is an X-ray telescope. Now you have to see that for certain wavelengths, we have to depend on space telescopes because space telescopes, yeah, because space telescopes are the only way in which you can observe what is outside the atmosphere, right? The atmosphere blocks radiation from X-ray, gamma ray, ultraviolet, etc. So to observe the universe in X-ray, you have to have a space telescope, and that is Chandra. Chandra is it's still very operational. The telescope is very operational, and you still get very good data. And there's the Chandra archive. You can click over here, have a look at the Chandra archive, and you can have a look at all the data that is available in this. It's a very good website, very good, right? So I think I covered Spitzer, Chandra, Hubble, and I think that's
yeah.
it.
Thank you. Yeah, that's good. That's good. Different wavelength bands, just to have an idea of, yeah, these data, they're being taken and they're actually pretty quickly made available as well to the community. So
yeah, especially if they're legacy, then it is immediately put. It's like,
yeah.
for example, Gaia data is immediately put online, right?
Yeah.
There is
Yeah.
no proprietary period. So this is
Exactly.
the good survey. So what we did is we used this data to actually study AGN. And how did we do it? What happens is the AGN are basically, they're very energetic things, and hence they will emit in X-ray. So what we did is we actually looked for galaxies in the Goods field. Now the Goods field is about the size of the half the moon, okay? 160 square arc minutes. That's the approximate size or the area of the Goods field. Actually this format changed, but doesn't matter. So the Goods field actually has an area of something like this. And what happens is, I'm sorry, but from Linux, I shifted it to this, so it actually changed. So what happens is, the problem is there are many more complications in this. And one of the complications is for the area 160 square arc minutes. In Goods, you have 29,000 sources, okay? But if you see the corresponding Chandra catalog, there are only 230 sources, right? So you have to actually cross-match from the Goods to Chandra, when you can see there's a factor of, it's a factor of how much? It's a factor of 100, the difference between the number of Chandra sources and the good sources, right? Now, so the problem is you have to actually look for counterparts, optical counterparts for the Chandra X-ray sources. And the other problem is that the resolution of both the telescopes is different for the Chandra telescope as well as the infrared telescope. So, sorry, for the HST. So therefore, what happens is the closest match need not be the correct match, right? So for every source, if you have 100 matches, the closest one is not this thing. The brightest one also need not be. And therefore, it's a little complicated. Here, I've actually put it. This is the Goods field, and you can see these are the Chandra sources, the dots, which are actually showing you how many Chandra sources you have over here. And therefore, it's not a very easy job to actually find the counterparts. So we used some methods. I'll share the paper, I can share it with you, but we used some clever techniques to actually find the counterparts. So you need to understand that in many of these problems, there are smaller things which also need attention, and you need to carefully think about how do you actually select a counterpart for the source, right? Because if you wrongly connect the counterpart, you will study the wrong source. Simple as that. So what we did is for our 230 sources, we had 164 with counterparts. We still had some for which we had counterparts for which we could not figure it out. And there were 20 sources for which we did not get counterparts. So such a thing can happen, right? Not everything is so direct, right? So that's what happened. So, and again, we have to use spectroscopic data. Why do we use spectroscopic data? Because we can get the redshifts for each of these galaxies, right? So for Goods data, there was FOSS2 spectroscopy, which was available. for that area, and therefore for some of the objects which we had, we could actually get redshifts, right? And the first two spectrograph is an excellent instrument. The uncertainty in redshift is in the third decimal place, right? It's so good. The next step which we did is we did galfit decomposition. But now when we decompose galfit, what we actually had to do, sorry, this was actually an animation. Okay, what we actually had to do was we had to break it into the bulge and the disk, and more importantly, the point source, the central point source. Now, generally the problem with AGN is that because the central point source is so bright, you cannot see the galaxy at all, the host galaxy. And therefore, we are cutting bit by bit. We cut the bulge, we cut the disk, and we cut the point source. The central point source also has to be cut off, has to be accounted for. So here you see these are the profiles of the different Cersec indexes, right? So when we fit it, you may get different Cersec indexes. For example, the highest Cersec index is 5, which is this one, and the lowest Cersec index is over here, which is for 0.2. The one when you have this one is the one, which is the green one. So when you fit it, you may get different Cersec things. And here, this was not there in the previous one, but you can see that, for example, if you have an exponential profile, the profile looks something like this. If you have a 1/4, this 4 is called a divocular profile. So divocular fitted to 1/4, and this is typically for elliptical galaxies, which he got profiles of this kind. So you can get different profiles, but basically we decompose it. We decompose it so that we then get the properties of the host galaxy, right? And that's what we basically did. So here's another example. Here's the science image. This is the model image. This is the residual, and this is the point source, right? So we are here in this case, we are also modeling the point source because we want to subtract the point source because the point source is too bright. And if I have the point source brightness, I will not be able to see the galaxy. So I need to cut off the point source, not see the point source, and then I can look at the galaxy. So these are some of the images which we have for our sample. I forgot the sample is how many, again, some 300, 400 galaxies. And we had it in 2 bands, and therefore we got, these are called color maps. So with the color maps, you can see that you can very well, like if you were to see this image, you would not know whether these galaxies are related, right? This could be something else, this could be something else, this could be something else. But now with this, you can clearly see that all of them are definitely interacting, right? They are kind of, with each other. Similarly, over here, you can see more details. You can see this has spiral arms. I hope you can see it. There are spiral arms. And then you can see further structure, which you can see with the color maps. You can see knots. These are different knots which are there on the spiral arms.
So this is again, excuse me, Priya,
yeah.
This is again a result of applying the galfit, and then
this is color maps. So we did galfit also to get the morphological types, but we also did what are called color maps. So you put 2 images, one on each other, and you kind of subtract them. You get the color, so that you get up the colors so that you can see the red and the blue and all that. But the problem is you have to exactly scale both the images so that they sit exactly one on the other. So you kind of smoothen both of them to get the same resolution for both, so that you cut off and get it, right?
I see. And you say in the left image here, you say, okay, here you cannot tell if these structures are interacting or not, but then if you take the color, then you can, because they have the same color. Is that
exactly? Yeah. And then here, see, it enhances the features. Like you look at this, I don't know how well you all can see, but you can very vaguely see some structure. But now here in this, you can clearly see a structure, right? In the color map, you can clearly see structure. So this is kind of image processing, but it is, like I said, it's a color map. So it enhances the colors, and through that, you can see much more features. Basically, what we're trying to do is we're trying to see the morphology as best as we can.
Yeah.
Right?
Okay.
Because the morphology has these things. So actually here, what we also did is that since we had, the Goods field is a very deep field, very long exposure. It's a million, I mean, the Chandra one is a 1,000,000-second exposure, right? It's a very deep exposure. So therefore, what we did is we go up to redshifts of 1.3, redshift 1.3. And therefore, you can see over here that we actually have, what do you say? We've actually see this is the bulge to total ratio for different redshifts. So you can see for redshift range less than 0.4, this was the bulge to total ratio. You can see more, more bulge dominated. Then between 0.4 and 0.78, this is the distribution. 0.78 to 0.95, this is the distribution, and this one is this. So you can actually see the evolution also of AGN, and then basically the evolution of host galaxies of AGN with redshift, right?
Yeah.
Which, for example, in that one, Coma cluster has a redshift of only 0.02. So you're looking at very local universe. But here you're going up to 1.3 redshift. You're going very far in redshift. And therefore, you can actually see how do, like you see over here, these kind of galaxies are not there much closer over here. But in older redshift, in the older universe, earlier universe, oh, I forgot to, I think, to record.
Oi, no,
Oh,
I
no,
see
it's
that.
recording. It's recording. Yeah, it's recording.
Recording. Yes,
So
yes.
here what you see is you can actually see the evolution in redshift, right?
Yeah, yeah.
So
Right.
similarly over here, this is the same image over here, which you can see in different redshift bins. I've actually shown you how do the different kinds of galaxies, host galaxies, differ. So you can see in our early universe within redshift of 0.4, you can see a very large number of them are interacting merging galaxies. You have ESOs and you have spiral galaxies. This is the percentages. When 0.4 to 0.78, the number of interacting galaxies reduced, but the ESOs are large, spirals are here. And then as I go further in redshift, again, you see now the spirals have increased, much more spirals over here. And then over here, at larger redshift, 0.95 to 1.3, you almost have an equal distribution of interacting ESOs as well as of spirals, right?
Yeah,
So
right.
here you can...
Sorry, excuse me. That gives you an idea of how these galaxies actually transform in time, right?
Exactly. But these are only the AGN host galaxies. Right?
Okay. Yes.
We are only studying the AGN host galaxies and seeing how do they vary with redshift, right? How is it different with redshift for AGN host galaxies, right? Yeah. But one can do a similar study, for example, for all galaxies, right? I mean, for whatever sample of galaxies, you can do it and study it and this thing. Yeah.
Okay. Yeah. And just so the figure here on the right is linked to the figure on the left in the sense
it's the
that
same thing. Yeah.
The B over T ratio gives you classification as you showed before, eh?
Yeah.
Yeah. Okay. Thank you. One more question about B versus T, because it gives you an actual number, but the actual number, you get it from the fit to the galaxy itself. And so what exact parameters are those then? What determines the B and what determines the T?
Yeah, so galfit tells you what are the properties of the bulge. It will tell you what is the brightness, what is the radius, what is the that. So you use that to get, and you use you say that therefore that implies that the bulge is so huge because you have the radius, you have the brightness, etc. Similarly, the total part of the galaxy also you know that. So you get that from galfit. You need to do galfit to get the B by T.
Yes. Okay. Thank you.
So actually, it's a combination of galfit as well as the color maps as well as spectroscopic information. You combine them all. That's the idea. Yeah.
Okay. Interesting. Thank you.
So here we can actually see how have these AGN host galaxies evolved over time, right? So so if whatever theory one has about AGN, so basically you're seeing that AGN is happening in all kinds of galaxies, right? It's just that the distribution in redshift is different, but it can happen, and AGN can happen in an elliptical galaxy, in an SO galaxy, in an SP galaxy, in any kind of galaxy, right? And that's what our understanding of AGN activity is. Sorry, that it is an activity which is inherent in all kinds of galaxies.
Okay, yes. A question related to that, does it, so because the fact that now, for example, at shorter redshifts, lower redshifts, we see more AGNs in irregular or merged galaxies, does that mean that there are just more of those, or does that mean that for some reason now there are more AGNs linked to those?
So this is the proportion, right? So obviously in our nearby universe, in low redshifts, we are seeing it more in interacting galaxies. And that's what thank you. And we're going to come to that point that it was believed strongly that AGN probably could be merger driven, right? That because you have mergers, the merger causes AGN activity, right? And therefore, one of the results which we got from this paper was actually to infer whether AGN, is it happening because of mergers, right?
Yes.
And that's what we are coming to. Actually, the whole, my text size has changed. But what we basically found in this is that it is not merger driven.
Yeah,
It is
indeed.
not the bulk of these galaxies are not merger driven. Okay,
Yeah.
they are basically, you can see over here. So we did it for 192 galaxies, and the redshift range is zero point 0.4 to 1.3, and you can
Yeah.
actually see that the this AGN mechanism, what we found out was it was not merger driven. It was basically the galaxies are bulge dominated. They have large bulges, which are related to the black holes, which is fine, which is correct. But
Okay.
they are not merger activity. Otherwise, the earlier idea was that probably it is merger driven, but it's not.
And the reason how you can conclude that is because in the beginning or at larger redshifts you have more interacting or merger, and then it
Yeah,
declines, right?
yeah,
So
yeah. So you see, it's not. It's,
yeah,
you see this the larger. If you actually do it statistically, we did the test, and you basically see that they are essentially all ESOs. That's the
yeah,
bulk. So it's basically bulge driven and not merger driven.
yeah.
So instead,
O-
that was one of the important results of this, that we basically used data from 4 bands, and you basically found out that these AGN host galaxies are essentially bulge dominated and not interacting galaxies, the bulk of
okay.
them, right? It's
Yeah,
something ahead. So,
great.
but obviously, I will put a disclaimer over here, and the disclaimer is this. I'm sorry, I'm changing this because on Linux this was different. Now it's fine. So what you basically see is we have to also be careful, like astronomers, we don't jump to conclusions, that these results obviously apply to moderate luminosity AGN, right? Which have a LLX value of something like this. This is 10 cap, sorry, it should be 10 cap. And at this thing. So, and another important thing is that the good survey covers a very small angle, right?
Mhm.
And therefore we do not see many high luminosity AGN. And we should also keep our minds open that maybe the picture we are getting is a biased picture because we are
Mhm.
looking at a very small patch of the sky and with moderate luminosity AGN. But after this, there was another survey which was done, which is called the GEMS survey, Galaxy and Evolution from Morphology and SEDs. Okay. And in the GEMS survey, which is a much larger survey, they also studied the host galaxies of 15 optically selected AGN. And again, in their study also, they found that 80% of the host galaxies were bulge dominated,
Mhm.
right? So in
Okay.
principle, even with the GEM survey, they found this thing that AGN hosts are essentially bulge dominated and not uh, merger dominated, right? So
Yeah.
that was the important result we had from this paper. I think my time is up.
Yeah. Perfectly in time. Thank you so
Yeah.
much. We learned a lot.
Oh, thanks a
Um,
lot.
it's very, very interesting, and it really fits into the course here. So that's great. I
And this is
want
the reference to the paper. Sorry, Catherine, but here's the reference to the paper. So,
Okay, that's great. We can because I think we will Priya and I we can chat more, and we can decide also what would be things for the students to keep from this presentation.
mhm.
But before we round up, I'm sorry we are already 4, so I don't want to keep you much longer. But students, do you have any questions?
Let's see the chat. There's one
Yeah,
question, something in the chat.
yeah, I think it's something that I wrote.
Okay, good. Okay,
Yeah,
okay.
yeah, because the acronyms of astronomers are sometimes quite straightforward, like
Yes.
the Very Large Telescope, the VLT, or the
Yeah.
Extremely
Or the
Large Telescope,
extremely large telescope. That is so
or the overwhelming.
uncreative. Yeah.
Yes,
They
but
could have named it on some Greek god or something like that, right?
exactly, yes, but it
I think
works.
this has been
But
an
also have,
overdose for the students, maybe. Or they, anyway, they can always ask me questions anytime.
yes, yes. So students, feel free to ask questions now. I also please also maybe we can just open the floor so that we can briefly see everyone who can turn on their cameras so that
Mhm.
you see us again. So you can turn on your cameras again before we round off. So Priya can see you.
Yeah,
Thank
that'll
you.
be good. Okay. Oh, wow. So all these people do exist in the real world.
Yes, really there. Yes.
Yeah, because otherwise it's so difficult to, you know, uh,
Yeah,
okay.
to
Hello,
have an idea.
everyone.
To, so I would like to hear from you students, how was this for you? Was it too fast, or was it okay? Could you follow it? Did you learn something? Do you have questions, importantly? Feel free to speak up or to type them. Possibly also it was a lot of information at the same time. Maybe when you
Yeah.
will see it again, or when then you might have questions. No questions?
I think they're tired.
Yes, possibly. It's Friday afternoon, Friday evening for you. So
Yep.
so then thank you so much, Priya. Really, this was
Welcome.
very interesting.
Bye
It's
bye.
very great to hear from an expert who works specifically in these fields. So students, see you next week.
Catherine, actually, I work on stars.
I know. That's how I,
This
yes,
is a
but we
side business. It's on the side.
yes, yes. So you see also students that you can work in astrophysics. Sometimes if you're familiar with some techniques, you can apply them in different subfields. And I think Priya, you've been using many different techniques, right, in different subfields. I'm
That's
also
right.
very interested in the project you mentioned with the archival data. So if you have a bit more time, but I think dinner is coming soon for you, we can either we stay now for a bit, or we talk sometime later. So
Sometime later,
whatever.
let's let the
Yes.
students get some
Yeah.
uh,
Uh,
time to this.
and students, if we'll see each other next week, I hope to hear from those who haven't declared their topic yet, what you will work about. And yeah, the questions on this topic we will discuss. Priya and I will discuss them. And if you have questions, then I'm sure we can ask them to Priya later on as well.
Yeah, sure. Yeah.
Okay. Thanks so much. Have a nice evening and enjoy your meal. And
Yes.
see
Bye
you
bye.
soon. Bye.
Thank you.
Thank you.
Bye.
Bye.
Thank you.
It was very
Bye.
interesting.
Thank you. Bye bye. Should I?
Um, thank you. Super interesting,
Yeah.
Priya. And you can, but once you have the recording, you can see what's the best
Yeah.
way to get it to
Yeah.
me.
Yeah. I'll
Um,
upload it on YouTube, and that's it.
yeah,
That'll be the best thing. Okay.
that's great.
Yeah.
Yes.
Bye bye.
Okay. Greetings. Bye-bye. Thank you.
Bye.